Okay, so we were doing some analysis of this using first and second derivatives. We took the derivatives and we found, what did we find? Okay, so the domain was all positive values of x. We took the first derivative and we found out that the zeros of the first derivative were at 0 and when log x equaled 9. So when x equaled e to the 9th, right? 0 we discarded because it's not in the domain. So that's not a valid critical number. But e to the 9th was. We took the second derivative and we found out that it had a single 0 at x equals e to the 8th. And so here's where we were. We were filling out some stuff for our table. And let's see. We used the second derivative test on our critical number at e to the 9th, and we found out that the second derivative had a negative sign at that point, so that had to be a maximum. And then at e to the 8th, we had a 0 of the second derivative. What's really the only thing that we have left to do here on our table?
Test points?
Yeah, and I really just need one test point, don't I? Right, I was able to apply the second derivative test on my critical number to determine that that was a maximum. But now I just need to determine if this 0 of the second derivative is an inflection point, right? Is it a place where the concavity is changing? So I'll pick a point somewhere between 0 and e to the 8th. E to the 8th is a pretty big number. So what if we just plugged in something like, I don't know, like 10 or something, right? So we're going to evaluate the second derivative there. Our second derivative, here it is right here. So actually, why don't we pick, rather than pick something like 10, why don't I pick e to the 7th? Because I'm taking a natural log of that. That would make it a little bit easier, wouldn't it? Everybody see that? Because the natural log of e to the 7th would just be 7, right? Okay, so we'll pick a test point. And so if I evaluate the second derivative, here's my second derivative. If I evaluate that at e to the 7th, I'm going to get 32 minus 4 times the natural log of e to the 7th is 7. So I get a positive result, don't I? Okay, so then we know that this is an inflection point. That's a place where we're shifting concavities. Is there anything else we could do here? Not really. Not really. It looks like we have all we need to graph this thing right then. So we're concave up on this interval from 0 to e to the 8th. We're concave down on the other interval, and we have a maximum there. And so then, does it make sense that that's what we're looking at, isn't it? Right? No, that's not right. Oh, never mind. That's not the graph of this thing. That's a different graph. That's a different problem. So if we had to make a graph of this, we would get, what would we get here? I tell you what, I'm just going to graph it, and we'll just compare the graph to this table. Make this a little quicker. I'll graph it in Desmos real quick. Wow. What is, let's see what these numbers are real quick. So what is e to the 8th? E to the 8th is about 2,980. Okay, so if I zoom out a little bit there, I just want to, so what would I do here? This is a practical question. What would you guys do if you want to see this graph better? Suggestions. How do you use this graphing utility to see this thing? I mean, what's the problem?
It's too tall.
It's too.
Use the little tool icon to shrink the y-values.
Yeah, it's way too tall, isn't it? Right. So can we? There used to be a way to do a zoom on this, but I don't know if there is anymore. No, there isn't. It used to be kind of cool. There used to be a zoom feature on this. So we're going to leave the X's alone, but we're going to let the Y's get a lot bigger. I'm just going to go into the tool and I'm going to manually adjust the window. So what is that now? It's something like 10,000. Let's have that go up to, I don't know, 500,000, see if that works. We're getting there. If I add another 0, maybe one more 0. Okay, so now I'm just pretty close. How about if I just come back, instead of making that 500,000, let's make it 200,000 or 100,000. There we go. Okay. So now we can see things a little bit better, can't we? Okay. Does that match? Does that match our picture? You know what? Maybe I will. Ten to the 7th. Nine. Okay. Does that match our picture? That's doing what it's supposed to do, isn't it? It's concave up here, right? We have it flips at some point from being concave up to concave down, and we get our maximum. If I just, maybe I can just do this. There, that fits pretty well. So then we get our, oh, darn it. There's our maximum, and then it's concave down everywhere for the rest of the function, right? So yeah, that fits. Okay. Any questions on that? Does that make sense? Okay, and could we graph that thing? Sure. All we'd have to do is just maybe attach some points to this. Like we could take a limit as x approaches 0. We could plug in e to the 8th, plug it into our function and make this an ordered pair. Plug e to the 9th into our function and make that an ordered pair, so we knew the y values, where they would go on the graph. And then we could just use the shape of the graph to fill in the blanks, right? Okay. All right, so we're going to get into some more normal ones now. We're going to look, hopefully we'll get to the point we're going to really focus on graphs of rational functions. Those are really, there's a lot of learning to do with those. There's a lot of things to consider, and if you get good at graphing rational functions, you can do lots of other things too related to that. So let's take a look at this guy here. This is just a kind of a warm-up thing for us. Use the graph of the function f to estimate where f prime and f double prime are 0, positive, and negative. So try this one real quick. See, think about this and maybe type in chat, where is f, using interval notation, where is the first derivative positive? Just roughly. Maybe we can go faster on this one. This one's pretty easy. Where's the first derivative? Go ahead, Seth. Where's the first derivative positive?
Like negative infinity to like 3/4, and then 3 1/4 to positive infinity.
Okay, good. So negative infinity up to whatever that x value is. Who knows what that is, right? Some decimal less than 1. And then, or, we have to say or, from that x value, which is like, what is that, 3.2 or something, up to infinity. Everybody agree? That's where the function's increasing. And where is it decreasing? Well, in between those two decimal values, it would be decreasing. Okay, roughly speaking, where is the second derivative positive? And let's assume that the answer is a convenient one here. Where's the second derivative going to be positive here? Natalie?
Is it from like 0 to 2?
No, where the second derivative is positive. Think what the second derivative does. Second derivative is concavity, right? Okay, Kirsten, you want to take a stab at that? Where's the second derivative appear to be positive?
Is it from 2 to infinity?
Yeah, there you go. Good. See, it looks like that's the point of transition, isn't it? It looks like this becomes bowl-shaped, bowl-shaped up at about 2, and then it'd be, the concavity would be negative to the left of x equals 2, right? Remember our little test for that. We'd have tangents to the curve would sit on top of the curve where it has a negative concavity, and they'd sit below the curve where it has a positive concavity, okay? And it looks like we'd have everybody agree we have a 0 for the second derivative at about 2, and we'd have a 0 for the first derivative wherever we have horizontal tangents. Okay, true or false? Let's take this first example here, the top example. The zeros of f prime are -3, 1, and 4. So the local extrema are located at these points. For that to be false, you only have to be able to find one counterexample. True or false? Type it in chat for the first one. Just type in a T or an F, true or false, for that top one. True or false? Everybody weigh in on that. If the zeros of the first derivative are at -3, 1, and 4, are the local extrema located at those points? Okay, but we can make no assumptions about this. This is saying that if those are zeros, then local extrema exists there. True or false? Okay, looks like we agree it's false. So how come? Somebody articulate a reason here. Why is that false? What's the counterexample we could offer? Johan, what's the counterexample?
I'm not entirely sure.
Okay, what could happen there, somebody? What could happen there? How could we have zeros of the first derivative that are not local extrema or relative extrema? Local and relative mean the same thing, right?
You could have one of the points where it comes up and then levels off and then keeps going up.
Okay, yeah. Okay, it could be an inflection point, couldn't it? Yeah, it could be an inflection point instead, right? So we're false there. Okay, yeah. Right, so it could just do something like this. What if we had the function that just went like that, right? Okay, how about the second statement? The zeros of the second derivative are -2 and 4. So the inflection points are located at these points. True or false? In other words, that's just a sneaky way of asking you, are the zeros of the second derivative always inflection points? Okay, so I'm getting lots of false here. What's an example of a function where did we see that? Can everybody give me an example of of a simple function where we could have zeros of the second derivative that are not inflection points? Okay, remember the example we did. I don't think I did. I put this one in here? No, I don't know if I did. Remember the example. Oh, I have to do this. Remember the example we did where we had x cubed and x to the fourth, right? If I take x to the fourth, for example, if it's an even function that has a large exponent, then f prime of x equals 12x cubed. F double prime of x equals 36x squared, right? Well, the zeros of all the derivatives are 0, aren't they? Right? So if we made a table out of this, remember doing this? Right, we had 0 was a 0 of the function, the first derivative, and the second derivative, right? But we know what that function looks like. X to the fourth just looks like this, right? It just looks like that. It never changes concavity, does it? If we look at signs, if we pick some test points, like at -1 and +1, well, the second derivative is positive everywhere, isn't it? Except at 0. So there's an example. That's false, isn't it? Okay. The moral of the story is we can't assume that zeros of the second derivative are inflection points. We have to check that with test points in our table, right? Okay, everybody give me 1 to 5 on that. Does that make sense? Okay, all right. So the zeros of, last example here, the zeros of the denominator of f are -3 and 4. So f has vertical asymptotes at these points. True or false? The zeros of the denominator of f are -3 and 4. So f has vertical asymptotes at these points. Okay, Ember, you're correct. How come?
I don't know if this is right, but couldn't it possibly be a slant asymptote?
Zeros of the denominator. No, can't be a slant asymptote. But there is something it could be. Think about, now let me ask you another question, just a clarifying question here. So zeros of the denominator, if we go back to Algebra 2 or the start of the year, we reviewed this a little bit. What are the only things that zeros of the denominator could possibly be? There's only two choices. If I have a zero of the denominator, either it's this or that. What are the two possibilities? Andy, what are the two possibilities?
Holes or vertical asymptotes.
Ah, okay. Holes or vertical asymptotes, right? They could be either or. Now, what are the conditions for a vertical asymptote? Do you remember, Amber, what the conditions for a vertical asymptote are? It's a zero of what? Anybody want to fill in the blank there? What is that? The conditions for a vertical asymptote.
Zero of the denominator without being a zero of the numerator.
Okay, so it's a unique zero of the denominator, right? And I have to clarify something there too, because the books don't always state this, but it's a unique zero of the denominator after the function has been simplified, okay? A whole, on the other hand, is a shared zero of the numerator and the denominator, right? Does that make sense? Okay, so let's look at a couple quick examples here. So, like, what if we took f of x equals x squared over x, right? Well, that's undefined at 0. Clearly, that's a whole, isn't it? Right? Everybody agree? Okay. However, this is the one where I think a lot of times people make mistakes on this. What if I take the function x over x squared? 0 is a shared zero of the top and the bottom, but that clearly gives us a vertical asymptote. So what's the difference? What's the difference there? If I simplify that function, f of x, if I rewrite it as a simpler function, what does it look like, right? This just looks like one over x, doesn't it? Right? And we already know that, x cannot equal 0, but it looks like the 1 over x function. And if I graph those, what do you think is going to happen if I graph f of x or g of x equals 1 over x? They're going to line up perfectly, aren't they? Right? They are algebraically equivalent. So if I simplify this function, this is a case where I can see that 0 becomes a zero of the denominator, but not the numerator, if I cancel like factors. Everybody get that? That's a really easy one to miss, because you might, at first glance, you might think, okay, that's got to be a whole because it's a zero of the top and the bottom. How is that different from this previous example? The previous example, well, what happens if we simplify this, right? If we simplify this, we end up getting x squared over x equals x. But remember, x still can't equal 0, so we actually get a whole there, right? Because in our original function, we had to exclude x from the function, but it just looks like the line y equals x. Well, x over 1, that's a situation where, we don't have a 0 of the denominator, right? So that one becomes a whole because it simplifies to a function that doesn't have an asymptote there. Everybody get that? Okay, see the difference, right? Okay, any question? Give me a 1 to 5 on that. Okay. Okay, once again, how would you know? Well, if I simplify this, the 0 of the denominator disappears. So therefore it's a whole. Whereas if I simplify this guy, let me just do that. The 0 of the denominator does not disappear, right? So I get an asymptote. Okay. All right, moving on. Sketch a curve with the following properties. Let's just kind of walk through this, right? So we've got these different intervals of our domain where it's giving us the signs of the first and second derivative. Okay, so when x is less than -1, the first derivative and the second derivative are both negative. So what's that mean, right? It's first derivative is negative means what? Type that in chat real quick. The function is what? First derivative is negative. Okay, good. So it's decreasing. Good. Second derivative is negative. What does that mean? Okay, concave down. There you go. So then that must look like that, right? Everybody agree? Decreasing concave down. What about the next interval between -1 and 0? It's still decreasing because the first derivative is negative, but now it becomes concave up, right? And so, whoops, there's 1, I guess. And so now it's going to continue to decrease, but the concavity is bowl-shaped up, right? Okay, so then what's going on here at 0? This is a place where the concavity is remaining positive, but the function transitions from decreasing to increasing. So what is that? What's happening at x equals 0? Okay, good. That has to be a minimum, doesn't it? Right? By either test, first derivative or second derivative. By the first derivative test, we know that to the left of 0, the function is decreasing. To the right, it's increasing. A transition from decreasing to increasing by the first derivative test is a minimum. If that's presumably that's a 0 of the first derivative, right? Because it's transitioning from negative to positive, right? And we're sketching a smooth curve here. So we know that that's at x equals 0, the first derivative is going to equal 0, and yet the second derivative is concave up. By the second derivative test, that's a minimum, right? Okay, so now we go up to 8. Now what's happening after 8? The first derivative remains positive, but the second derivative shifts from positive to negative. What is that? What's happening at x equals 8? So we're transitioning, from this row down to this row. Okay, yeah, that's an inflection point, isn't it? Good, right? Continues to increase, but the concavity shifts. And then finally, what's happening at 10 here? At 10, the first derivative is remaining positive, so it continues to increase, but the concavity is shifting from negative to positive. So what's happening at 10? What's happening at 10? Okay, good. Yeah, another inflection point, isn't it? Good. Right? That's what it's got to look like. Okay, everybody good with that? We're making those connections? Okay? Okay, another just theoretical question, kind of a head scratcher here. Suppose a continuous function f is concave up everywhere except 0. Assume that the function f has a local maximum at x equals 0. What, if anything, do you know about f prime of 0? This is a tricky one. I'll let you think about this for a second. What do you know about that? If the function is concave up everywhere except 0, and it does have a local maximum at x equals 0, what do you know about the first derivative of the function at 0?
Can it not exist?
Say it again.
Can it not exist?
What's your thinking?
What I'm imagining is, I don't know if I can describe this, but like a parabola where it dips down below zero and then comes back up on both sides, has like a cusp.
Okay, yeah, it's
Right?
that's exactly right. It's got to be a cusp, doesn't it? Right? Because if it's, think what we know here. We know that it's concave up everywhere except zero. It has to have a local maximum. Well, how could you do that? You can't have, you can't have upward concavity with a local maximum, right? Unless it's doing something like this. Right? It's got to be doing something like that, where it's concave up everywhere. We've got a sharp corner there. And so we can see that the function, that's the only way we could get a maximum out of that, right? Does that make sense? So it would have to be the derivative doesn't exist because we got a sharp corner. Okay? All right. Questions? What are you laughing at, Kyle? Okay, moving on. I'm going to skip through this one. We'll do that one later. Okay, quick reminder, and I'm sure you guys know this, but just quick reminder, with rational functions, remember that if the degree of the numerator is less than the degree of the denominator, when we take our limit at infinity, remember that's where it goes to zero, right? And we'll review that stuff when we apply it. If the degrees of the numerator and the denominator are equal, then the limit at infinity, positive or negative infinity, is equal to the ratio of the leading coefficients. Is this ringing a bell? And if the degree of the numerator is greater than the degree of the denominator, then we don't have, the limit doesn't exist, right? The thing's not going to have a fixed limit, okay? And we'll look at each of those cases as we get to them, but there's just a quick reminder. So let's look at something like this then. We want to use a table to do everything for this. And I've actually included, we're not going to get through this today, obviously, but we'll get started. I've included on the assignment, and this will be on the test too, these are all the questions that you're going to have to answer for these functions. So I want to make sure we go through these in class so you just are aware, how would you enter these on the assignments or the test. Okay, so let's take this guy. All right, first of all, let's talk domain. Okay, what's the domain of this thing? Type it in chat, everybody. What's the domain? Okay, good. Kyle, why is it all reals?
Because on the bottom there's that +3, and so it makes it so it's like never 0.
Okay, good. Bottom is never equal to 0, so we're good. So the domain's all reals. Okay, what about, let's look at symmetry. What about symmetry here? Does this have odd symmetry or even symmetry or neither? And you're probably going to have, you may not be sure about the answer to this one. We haven't talked about this very much, but I want to start talking about it now. Continue talking about it. Wow, you got it. It's even. Okay, how come it's even? Somebody, how come it's even? Let's see, Daisy, why is it even?
Because if you plug in a negative and you square it, it's going to be positive. And it's positive, it's going to be positive.
Okay, good. So if I plug in negative, if I substitute negative x into the function, nothing changes, right? Everybody agree? Okay, good. I want to ask you another quick one here. How about while we're on the subject, what if I gave you a slightly different function? What if I gave you something like this? What if I said y equals x over x squared minus 3? odd, even, neither. What do you think on that one? Okay, it is odd. You're right. Good. Andy, why is it odd?
Because if it's negative on top and even on bottom, it makes the whole function negative altogether.
Okay, good. This is what we're now, we could just plug in negative x and just do the test, right? Would everybody agree here? If this is, let me call this f of x. Right. Darn it. Just get warmed up here. Bell rings. Holy smokes. Okay, well, we'll pick this up. You guys keep working. We'll just, over the next probably, I bet it's going to take us at least 2, if not 3 lectures. We'll just go through some examples. And somewhere along the line there, I put up the first assignment. I'll put up the second one. I'll put it up soon, but really the first one is the one you're going to want to tackle first because it's the one that deals with rational functions. Okay, and that's what we're talking about now. So have at it. I'm here after school if you need me. Otherwise, I will see you on Thursday. Have a great day.